Well, it's really nice to see a bunch of friendly faces here and meet a few new people. I'm going to be talking about wine oxidation chemistry. So at the end, there'll be a short quiz. To start, I want to mention this work was not done by me. It was done by a bunch of other people we've been collaborating with. Some of them you know from working from their presentations earlier today, and some others from my lab. This is the first question. So wine oxidation occurs through a number of very discrete steps, and a lot of the work we've been doing is trying to analyze what are those steps so we can understand what are the key control points and understand how to give you better tools in managing oxidation. And so this work, the work I'm going to be presenting is not really get into this, but I'm going to show you a little bit. You refer to this to explain some of our results. So when oxygen comes into wine, you have to have a catalyst. Oxygen will not react with organic molecules alone, and that's lucky for us because otherwise we'd all catch on fire. Sitting here in the room, because we have all this oxygen around and we're made of organic molecules. So our bodies control the oxidative process, and we manage that, in fact, the same as wine does in a way. We use iron as a catalyst, and that's why you've got hemoglobin in your blood that catalyzes that oxygen. So oxygen comes in, you need a catalyst, so it's usually iron, can be copper or manganese. And then this step here is a little bit mysterious. We haven't been able to nail down the presence of this intermediate. So it may or may not exist. But at any rate, we have the one step, and at the end of the first step, we get quinones and we get hydrogen peroxide. So one of the key things is understanding, okay, what happens to those two components? What happens to the quinones? And the quinones can go on to cause browning, for instance. So browning would arise from quinones. Also reacts with thiols, so if you have hydrogen sulfide around, you want to get rid of it, you add oxygen during fermentation, you generate a little bit of quinone that scavenges the hydrogen sulfide. If you're making Sauvignon Blanc and you want that New Zealand type character, you're avoiding oxygen because that thiol that you want in that wine, that 3MH, will react very quickly with this quinone and be lost. So sulfur molecules react very quickly with quinones. At any rate. So, and then we can put other things in here to prevent loss of those, and I'll mention some of those later. So just in terms of managing the process, we put antioxidants in, and what they do is they don't block the oxidation reaction. What they do is they remove the quinone before it reacts with other stuff. And then we get hydrogen peroxide. And again, hydrogen peroxide is you would obviously think of it from the name, it's got to be an oxidant, right? But again, alone, it's not terribly reactive. Some of you probably have hydrogen peroxide in bottles at home in the bathroom, to put on wounds, right? So it'll sit there for months, maybe even years. But with a catalyst like iron, then it decomposes almost instantaneously. If you put some iron salts into your hydrogen peroxide, it'll actually bubble a little bit. There's so many oxidation reactions occurring. But sulfur dioxide is a very good reducing agent, reacts with hydrogen peroxide very quickly and can remove it. And so this is one of the ways, again, that sulfur dioxide protects wine from oxidation, is that it removes this oxidant before it goes on to the next step, which is this reaction, and this is called the Fenton reaction. And this radical here will react with every organic molecule, period, and react almost instantaneously. So if this reaction goes, then antioxidants don't help. The sulfur dioxide will not capture this. Nothing will capture this. It just reacts in proportion to the molecules available. What that means is that it reacts most of the time with ethanol. Because aside from water, ethanol is about 90% of the organic molecules. So that's why you have acetaldehyde as a major product of oxidation, because when this reaction occurs, then it oxidizes whatever's there, and whatever's there in wine is mostly ethanol. And so we get these aldehydes. Acetaldehyde, of course, is the major one. It comes from ethanol, but everything else is oxidized. So Tartaric acid leads to glyxylic acid, which is well known to lead to good color stability. The other organic acids react. Sugars react, but nobody wants to study that because it's the black hole of chemistry. So it's too complicated. You can't figure it out. But at any rate, everything reacts in proportion to its concentration. And then you get these other products and so on. So I'll refer to some of this as I go along. So in terms of managing wine oxidation, the oxygen is consumed. So if you get oxygen in, so last talk we heard mostly about how to keep the oxygen out or what you should be doing to keep the oxygen out. But once you get it, okay, then you get quinones, you get the Fenton reaction, and then really that's what's the chemistry of managing that beyond that. Now, in order to study this scientifically, we wanted to measure the amount of oxygen that's consumed in. So we're going to talk about a bottling experiment. We want to measure the amount of oxygen that's consumed by the wine, okay? And how can we do that? So I think you've already heard some good information on how measurements can be done. And in order to study this, what we need to know for a particular bottle how much oxygen came into it. And so we need to know the amount of oxygen at bottling, the amount of oxygen that comes from the closure. So if we have a stopper, like a synthetic cork, that contains oxygen most of the time. And then, of course, we have oxygen transfer through the closure. And then if we know how much oxygen got into the wine, and then we look at the residual oxygen, then the balance tells us how much oxygen that wine consumed. So most of the time, in fact, all the times, oxygen is coming into the wine, and unless you've had a catastrophic event like a poor bottling episode, then the oxygen levels are very low, right? Because the wine is consuming the oxygen through all those reactions I just showed you. So the consumed oxygen is, generally speaking, the amount that's come into the wine. And then if you just bottled, you'll have some residual oxygen. You have to subtract that because that hasn't been consumed yet. Okay? But the question is then, how can we measure oxygen entering the bottle? And this is one method. There are a few other methods out there. You've probably heard of MOCON if you've done closure trials, or maybe you've heard of that. But at any rate, this is a technology that Nomocork has developed, which is really quite good. And you take a bottle, and so the key thing to realize is that we're not doing this on every bottle in the experiment, because you do this with some closures, right? And then you project onto your experiment, because you cannot measure every single bottle because, of course, the oxygen that's coming into the bottle is being consumed by the wine, and so you can't measure that, okay? So what we do is we take some closures which are reproducible, and here HP means high performance closures like a synthetic Nomocorks, which is fairly reproducible, okay? So if your closures are not the same one to the other, then this technique doesn't really work. You have to have consistent closures, okay? So what we're doing is we put a closure in a bottle, we fill the bottle with nitrogen, then we put the closure on, and then we watch oxygen appear, okay? And that tells you how much oxygen is coming into the bottle. So we have the oxygen here. You can see in the early first few days, oxygen level rapidly increases. That's because the closure itself has been compressed, and the oxygen in the closure is going into the bottle, right? And then at some point, that ends. And what you have is you have the steady state amount of oxygen permeating. Is it permeating or diffusing? Yeah. Okay, I think it's permeating through the closure, right? And then that's what you see here. So this is the amount of oxygen measured inside the bottle with one of the dots, one of the little dots, the NomoSense dots, right? So we can monitor this bottle over time, and we see the amount of oxygen in that bottle gradually increase, okay? So that tells us for this closure, right, how much oxygen is going to go through it. And in this experiment, they actually ran 3 different closures of 2 types. And you can see that from this data, the amount of oxygen coming through is nearly identical. So this is 3 at this point, what were called premium and classic. So we have data. Now this provides us data for any other bottle sealed with a premium or a classic, how much oxygen is going to come in. Okay, and that's the number we're going to use in our subsequent calculations. All right, so we're not measuring for every bottle how much oxygen is coming in. We're measuring it with a test system, right? And then we're going to use those numbers in our experiment. Because like I said, we can't actually measure this because if you have wine in the bottle, it's consuming the oxygen, so you don't see it accumulate. So this is a test system that shows how much oxygen comes into the bottle through that closure. I think I have some doubts out there. So if we're going to calculate, I think I've gone over this, to calculate the amount of oxygen that's come into the bottle, we have to know the amount of oxygen entered at bottling, which we'll measure immediately after bottling. Then we have the oxygen that comes through the closure, which we are estimating through that prior trial on similar closures, right? And then we have the current oxygen, which we'll measure in that bottle, okay? So the balance then is the oxygen that's disappeared into the wine. We're saying that's the oxygen consumed by the wine, okay? All right, and we're going to apply that to our experiment. So our experiment was to look at a wine and look at different treatments. So we have essentially 4 different wines here. We have wines in an oak barrel versus a stainless steel barrel. And we had a wine with lees and no lees. And then we had 4 closures, okay? So we essentially have 16 different wines. Now let me explain the closures here. So we actually had 2 different closures, but with one of them we had a premium which lets in less oxygen. And so that's different from light. And then we put the bottles with some of the premium closures into metal barrels, and we purged the air out of those barrels, and we put in either 4% oxygen or pure nitrogen, okay? So in theory here, this closure here should have no oxygen coming through once the oxygen gets out of the closure, right? There shouldn't be anything coming through into the wine. And since we totally screwed up the bottling, we decided to call this an accelerated aging experiment. This was our very first bottling trial, which actually we did use a commercial bottling line. But at the end of the day, we had so much oxygen in the wine that it would have been off all her charts. It was that bad. Anyway, but it did give us an opportunity, to look at what happens when you have a lot of oxygen that comes in, and we have some interesting data as a result. Okay, so what did we measure? So we bottled all this wine, and as you'll see, the DOs are shockingly high. And then we measured oxygen. We measured carbonyls. This would mean aldehydes, various aldehydes, acetaldehyde, pyruvate, and so on. Measured phenolics. We measured SO2. We measured some other things, but I'm going to talk about that data. Okay, so here's one of the 4 wines. So this is, and I'm not going to show all of them. They're fairly similar. This is Chardonnay wine in barrel with no lees. Okay, so we have a similar graph, four similar graphs of the barrel with lees, the barrel, the stainless steel without, and so on. And so what you see here is the dissolved oxygen goes down as you'd expect. It was surprising to me, especially over here, that the oxygen wasn't just disappearing faster. But with this particular wine, it was very slow to react with the oxygen. It took almost 200 days for that oxygen to be depleted. But as you can see, you're starting about 4 to 5 ppm oxygen, which, like I said, would be off the chart. We've been an outlier in her study, right? And this is headspace, and this is actual measurement. This is not total package oxygen. This would be higher. But anyway, you can see that these numbers go down fairly close to zero. The one that doesn't really go to zero is this one here, which is our light closure. Okay, so it's letting in, because this wine consumes the oxygen so slowly, and you can see it's a very slow oxygen consumer, that even the steady state amount of oxygen is actually measurable, that it never really goes to zero, because the small amount coming in is still enough to lead to some oxygen accumulation that we can measure. All right, and so then taking into account those measurements, right, with the residual oxygen in the bottles, and knowing how much oxygen would come through the closures, right, we can then calculate the amount of oxygen that's been consumed by the wine. So I'll just draw your attention to 2 points here. This one here is the premium under nitrogen, okay? And what I'm happy to see, even though we had plenty of oxygen to consume once we got it bottled, right, that after that oxygen was consumed, there was really no more activity, right? I mean, the wine consumed all the oxygen, and because the bottles are under nitrogen, right, there's no more oxygen coming through, and there's no more oxygen being consumed, right? Here with the light, though, we have oxygen continuing to be consumed. Now, if we went farther out, it would be interesting to see what would happen. Perhaps oxygen would start accumulating in the bottle more, but we're consuming most of the oxygen coming in. And this is the free SO2 data, and you can see the free SO2 data is getting pretty low here. And this is the light. You can see the numbers getting very low at the end of a year. So we're consuming a lot, if not all, of the SO2 available. Now, as I mentioned earlier, SO2 does not react directly with oxygen. But if you look at how SO2 will react with the quinone and the peroxide and so on, mathematically, you can still use the basic stoichiometry of SO2 and oxygen to estimate how much SO2 should be consumed. So what I'm saying is, forget about all the mechanisms. If we know how much oxygen is coming into your bottle, and if we expect the SO2 to act properly as an antioxidant, then we can predict how much SO2 should be lost, right? So 2 molecules of SO2 are required to react with 1 molecule of oxygen, and this is actually sulfate. So the SO2 is turned into sulfate in practice in wine. This is actually SO3, which is a noxious, it's the anhydride of sulfuric acid. Believe me, you don't have this in your wine, you just have sulfate. Okay, but for stoichiometric calculation, this is a good number to know, and then that means that 4 milligrams of SO2 will be broken down by 1 milligram. So 4 milligrams per liter of SO2 will be consumed with 1 milligram per liter of oxygen into the wine, assuming that the SO2 is the ultimate reactant with all those oxidation products, as it should be, right? So you're going to lose that 4-to-1, okay? And so if you lose the 4 milligrams of SO2 for every milligram of oxygen that's consumed, okay? So I'm getting back to this consumption issue. So if we can measure how much oxygen is consumed by the wine, and we can see that 4 milligrams of SO2 is consumed per milligram of oxygen, then the SO2 is acting as a perfect antioxidant. It is consuming all the oxidation products, okay? So what did we see with our data? That's why we're getting all these numbers. We want to see what's the ratio of oxygen coming in and being consumed versus the amount of SO2 that's being consumed. Okay, so we have oxygen being consumed, and then we want to match that with the SO2 being consumed. All right, so how is the SO2 being consumed? I'll just mention this again. The quinone then reacts with SO2 and converts it back to the starting material. Here, the peroxide is converted to water. So that's basically the 2 reactions that would, if we had enough SO2 there and it was working right, then the oxidation would be gone, right? By the action of SO2. Well, here's a graph of those ratios. Now, I'm going to draw your attention. This is the Chardonnay that was under nitrogen, right? So I mean with the closure that was under nitrogen. So this is the premium closure under nitrogen, and at least in one of these cases, the ratio was 3, which was pretty good. Okay, so what this means is that most of the oxidation was consumed by SO2. Okay, if we had a perfectly balanced situation, this number would be 4. Because we introduced so much oxygen in a hurry at the beginning, we ended up with some oxidation. So the balance of this is oxidation products, right? So oxidation products were appearing in this wine. And then this is, this is the samples with the light closure, okay? And you can see the numbers here are actually around 1, which means that most of the oxygen coming in is actually leading to oxidation products that are not consumed by SO2. And in fact, yes, these wines did taste oxidized, okay? So I'm presenting this in order to propose, essentially, that one way to measure whether or not your wine is being oxidized or not is to look at this ratio in your wine. Now, it's not, unfortunately, there's no meter that we can use to give us this number, which we would like. You actually have to let the wine age in a bottle and then look at SO2 loss versus expected consumed oxygen. But in fact, it's a very good way of measuring whether or not, in this specific case, whether or not the SO2 is working as an antioxidant or not, okay? And here we can see that in this case, so much oxygen is coming in that the SO2 can't keep up. These wines were down to about 4 milligrams per liter free SO2, and we're definitely getting oxidized. Okay, so one of the other things we observed, aside from the fact that, of course, the closure with the high oxygen transmission was leading to more oxidized wine, was quite surprising, and that was that the lees-aged wine had a higher ratio, meaning that the SO2 that was there was consuming more of the oxygen. So this was kind of surprising. And I did talk to a few winemakers about this, and maybe you can comment on this. I've heard people say that, yes, if I age my wine in barrel on lees, that it doesn't oxidize as much after the fact, that it's somehow protected. And so that was, so I thought, well, okay, maybe we're not completely, it's not a complete fluke that we observe this. And the question then was, well, what is the benefit of lees aging that would allow the SO2 to be more protective, right? So it's kind of like, well, what is going on there? Well, one of the things we noticed in our analysis was that lees-aged wine had less pyruvic acid. And so this led us to some further consideration of what could be going on. So subsequently have observed a few other reports in the literature where people have mentioned or noted that, at least in the case of exposure to bacteria, that the bacteria actually tend to consume aldehydes and ketones. So acetaldehyde levels are lower in wine that's been treated with malolactic bacteria. This actually leads to lower or less color development because acetaldehyde is important for color development. But it appears that this aging procedure would allow the microbes that are present in those lees to actually break down or consume any aldehydes, or at least some of the aldehydes that are present. So you have lower levels of aldehydes and ketones, oxidation products in wine that's been exposed to lees or gone through ML, it turns out. So we didn't do that trial here, but we may have observed a similar result. Okay, so we did some other reactions looking at the reaction of quinones with various nucleophiles. And this is looking at the reaction of a quinone, which is an oxidation product, with SO2. And here's our control, and you can see the reaction proceeds nicely. We consume the SO2. And then if we add pyruvic acid, initially it reacts nearly as fast, and then the reaction really slows down. So what we think is happening here is this is one of the oxidation products that arises from oxygen exposure, and that it is, an acetaldehyde does a very similar thing. So it essentially is binding up the SO2 a little bit. In the case of pyruvic acid, it's called a weak SO2 binder. So it's like putting an acetaldehyde that's not very effective, okay? And what we think is happening here is the Lees aging, okay, is eliminating the bacteria, the yeast perhaps, are consuming these aldehydes and ketones, which would otherwise weaken the effect of SO2, slow down its reaction by this weak binding. So we think that the interpretation of the benefit, okay, of Lees-aged wine in terms of being more protected is in fact the SO2 that you put in there is more effective because it doesn't have these other molecules that weakly bind it. So you do the analysis and you think you have the same level, so you have like 30 parts free SO2. Well, it turns out in the wine that's not been aged on Lees, there's an accumulation of these aldehydes and ketones that actually inhibit it from acting as a good antioxidant. So it turns out, we've seen other reports, like I said, the malolactic fermentation actually reduces the level of these things as well. Now, in some cases, you want these compounds. Pyruvic acid and acetaldehyde help build color stability. So and you don't always want less of this. In some cases, you actually want those molecules there, so you want to, that's why people are doing microoxygenation to produce these molecules, which then lead to color stabilization reactions. Okay, so this just explains in diagrams what I just said, is that we have, this is a little model of pyruvic acid, and with SO2 around, it forms a bound type. And then if that's not there, then we have SO2 available as an antioxidant. So it'll do things like convert quinones back to the phenols. Okay, so it's effective when it's a free molecule, but if it's bound with pyruvate or something, it doesn't work as well. Okay, and so these are some of the weak SO2 binding agents. We're continuing to work on, other experiments, try to better define these and figure out, how much do they bind and so on. And so hopefully in the future, we'll be able to give you information to allow you to predict. So if you get an analysis of some of these things, you could then have a better idea how effective your SO2 is going to be in protecting the wine. So I think I've already said that the barrel aging on Lees leads to lower levels of pyruvic acid. And then so the free SO2 as currently measured is actually just more effective. It's not bound up by some of these things. And so during oxidation, so the SO2 essentially works better, right? So you get a higher ratio of SO2 versus oxygen consumption. All right. And we think this ratio might be predictive of wine's protection. Unfortunately, you need at least 2 time points, usually if under bottle conditions far apart, like maybe 6 months or something to get those numbers. So maybe this won't be a terribly practical method, but it does seem to directly measure whether the SO2 you've put in bottle is actually protecting the wine or not. All right. So we're trying to come up with some better measurements of this available SO2. Maybe not free is the right word, but available SO2. And that's one of the basic projects we're working on, trying to figure out, is there a different way we could measure SO2 that would be more predictive of actual available and protective SO2. So I think TCO is a great way to measure what's actually happened in the bottle, how much oxygen the wine has consumed, and then comparing that versus SO2 gives you actually a real measurement of has that SO2 protected the wine or not. I can say we have other experiments where we have seen, and we actually did a better bottling too. We actually saw ratios around 4, and in some cases actually with wines that were under nitrogen, we actually saw ratios higher than 4, which we can't explain yet. But clearly the SO2 must be breaking down in some other manner, which we can't really explain, as I said. Anyway, and so one of our conclusions is that these measurements are useful in terms of helping us and you understand how SO2 is protecting the wine or not protecting the wine, and we think that free SO2 measurements need a little bit of improvement to be more predictive of how effective the SO2 is in protecting the wine. And thank you for your attention.